Students, colleagues and friends, welcome to this new course called the Quantum Hall Effects. And the reason that it's called Quantum Hall Effects, usually you would see that it's written as Quantum Hall Effect. But here along with original Quantum Hall Effect, I would also like to talk about anomalous Quantum Hall Effect and spin Hall Effect, and that's why this plural is used along with the Quantum Hall effect. So that's effects, that's what it means. In this course, there'll be sort of a number of topics that are going to be taught. I'll introduce the topics in brief, but before that, let me tell you the motivation for this course. Quantum Hall effect was discovered in 1980. Which is about 100 years later than the classical Hall effect was discovered, and I'll talk about the the discovery in details. But this was the first example of what's called as the topological insulator that was first talked about. So the quantum Hall systems are the first examples of topological insulators, and that's why the effect and its associated phenomena are important. And then it sort of migrated from its original notion of applying a magnetic field in a 2D electron gas. It went on to various areas, such as you do not have to apply a magnetic field, and it's just important to break the time reversal symmetry of the system. And that's what quantum Hall effect means. I mean, the anomalous quantum Hall effect would mean that, and then when the time reversal symmetry is restored, that's will give rise to another kind of quantum Hall system, which is called as a spin Hall effect, and constitutes another topological insulator that is found in nature. I'll talk about the experiments as well. So just to give you a brief sort of overview of the course, the content of the course, we are going to talk about transport in mesoscopic systems to begin with. Then we'll give historical introduction to the Hall effect. We'll talk about first about classical Hall effect, which was discovered in 1879 by Edwin Hall. Then we'll talk about quantum Hall effect, its discovery in 2D electron gases, and the Hall resistivity and the conductivity, and the experimental sort of realization of 2D electron gas. We'll talk about the metrology, that how quantum Hall effect actually establishes from an experiment in the lab, establishes the scale of resistance, the fundamental scale of resistance, which is given by h over e square. And then we'll talk about the integer quantum Hall effect. In fact, most of the discussion we are going to talk about integer quantum Hall effect, excepting for one module or one unit we are going to talk about fractional quantum Hall effect. Then we'll talk about how to approach this problem, what are the Landau levels, how actually electrons in presence of a magnetic field, planar electrons, that is electrons confined in 2D planes, that gives rise to the Landau levels, and these Landau levels in principle have infinite degeneracy. And we'll also talk about the quantum of flux associated with it, and that is how the degeneracy is represented in terms of the quantum of flux. We'll talk about the Shubnikov-de-Haas effects, oscillations, and so on. And will among this understanding of the quantum Hall effect can also be achieved by Laughlin's argument of a Corbino ring, which he actually thought of as a quantum Hall pump. So disk geometry, it's a thought experiment, and it explains the presence of the quantum of flux and the integer number of electrons being transferred from the edge of the disk, the inner edge of the disk, to the outer edge, and that's called as a Corbino ring. We'll talk about that. We'll talk about the role of disorder and the presence of edge states, which are the signature hallmark signatures of topological insulators. We'll talk about Hall conductivity, how to calculate Hall conductivity, and from a linear response theory, and we'll talk about the derivation of the Kubo formula, and we'll see that how the whole idea actually falls in place by the argument of 4 people, Thouless, Komoto, Dennis, and Nightingale. And this is relating the Hall conductivity to the Chern number. And then we'll talk about the topological consideration, the Gauss-Bonnet theorem, the Berry connection, the Berry curvature, and also we'll go over from a 2D electron gas, and we'll start talking about in a lattice system, or which in as a sort of recent example will take graphene to be that lattice where we get linear dispersion near the low energy dispersion is linear near the Fermi level, and we'll show that the quantization of the plateaus and how graphene nanoribbons are will give rise to these presence of the chiral edge states. What we mean by chiral edge states is that at one edge in a nanoribbon geometry, in one edge the electron traverses along one direction, say towards the right, and in the other edge it traverses towards the left, and that establishes the bulk boundary correspondence. We'll also talk about fractional quantum Hall effect and how the fractional quantization of the Hall plateaus arise because of the electronic interactions, the Coulomb interactions. We'll talk about Laughlin wave function, and we'll talk about the solution of the Schrodinger equation now in symmetric gauge, because we have circular Landau levels here. Then we'll talk about fractional statistics, a bit on fractional charge, anyons, and braiding statistics, and so on. And we'll talk about spin Hall effect and spin orbit coupling. In particular, we'll talk about Rashba spin orbit coupling. We'll talk about this applications to spintronics. We'll talk about experiments in real materials and these mercury telluride and cadmium telluride quantum wells, and how a band inversion occurs there, which gives rise to a quantum spin Hall state, which is another state in addition to the quantum Hall state that we have will learn throughout the course. So, let me start with the first thing that we had decided to do, that is let's talk about generally about conductance phenomena in mesoscopic systems. So, let me start with the mesoscopic systems, and in principle talk about a few length scales of the problem that are important in the present discussion. Okay. So, what's meant by mesoscopic system? So, these are anything between the macroscopic and the microscopic or the nanoscopic systems, and we are mainly going to be concerned with these, the low dimensional systems. And these study of these mesoscopic systems at low temperatures, it has been one of the most studied fields in condensed matter physics in recent times, and there are a lot of advancement happened in the last maybe 2 or 3 decades on the fabrication techniques. So, we are able to fabricate low dimensional systems at low temperature and so on, and not only that, there are further developments of adding electrodes and studying the conductance. So, the conductance properties of these mesoscopic systems are of importance, and they have been everywhere in the study of condensed matter systems. So, and by conductance we mean resistance as well. So, it is the transport properties of these mesoscopic systems, and systems being developed and fabricated at lower dimensions and have dimensions of the order of few nanometers or maybe hundreds of nanometers. Those are available experimentally, and one can also attach electrodes in order to study the conductance properties. All right. So, why is it important? We have to understand that. And the reason that it is important is that, especially at low temperatures, the quantum mechanical phenomena can be well understood. So, what we mean by quantum mechanical phenomena are that those which relate to the the observation of quantized energy scales of the problem. And the quantized energy scales they come with a scale of h cross, say for example, or h cross omega. The energy comes with a scale of h cross omega, and so these conductance properties, they explicitly give rise to these. If there are modes available for the electron transport, then only the conductance will show a peak, else the conductance will show a plateau. It is something like that. So that is a very important thing, that if you can actually in the lab see direct manifestation of quantum phenomena, those are very interesting. And it is also important to understand that these at low temperature particularly, the conductance or the resistance properties are very different from Ohm's law. Ohm's law talks about the voltage being proportional to the current, and the proportionality constant is known as R, the resistance of the sample. However, and we know that there are parallel and series combinations of resistances that are available, and in these mesoscopic systems at low temperature, they do not obey those addition of resistance formula either for series or for parallel. There is one more important thing, that is these conductance features are proportional to the number of electrons that are present, or the number of carriers that are present at the Fermi level. In fact, that can be tuned. That is, this is called as the density of states. The density of states can be tuned using external gate voltages. And finally, which is very important, last but not the least, as they say, is that the interaction effects, disorder effects, and the scattering between the carriers and impurities and disorder and imperfections, that can also be studied in these conductance properties of these mesoscopic systems, or below the scale of mesoscopic systems. Right now, the discussion that we are going to have is not directly related to the quantum Hall effect. Okay, we will talk about that. We are simply talking about, quantum Hall effect is also measurement of resistance when you pass a current in the longitudinal direction and measure the voltage in the transverse direction. Here we are only talking about measuring the voltage along the direction of the current. So, we are talking about either resistance or the inverse of it as conductance. So, this is a general discussion that precedes the discussion on quantum Hall effect, a general one that will help the audience to understand how lower dimensional systems, these conductance properties or the conduction properties are important for us to understand. Okay. In this connection, there are a number of length scales that are present, and one of the most important length scale is it's called as the coherence length, and it is denoted by let us call it as L phi. You will probably see various definitions of these what is called as a coherence length and so on. So, it is basically just to tell you that it is the distance over which an electronic wave function maintains its coherence. That is, the phase does not change, even if it changes, it maintains a relationship between the initial phase and the final phase. So, there is a well defined phase, so to say. So, it is a distance over which the electron travels where it retains the phase information. Okay. So, that is called as the coherence length, and a related quantity is called as tau phi, which is called as the coherence time. So, this coherence time is called tau phi, and these L phi and tau phi are denoted by root over d and a tau phi. Now, you see that there is a clear deviation from Newton's law of motion, where the L is known to be linear in time, whereas this the L phi and tau phi, which are length and time, are not related in a linear manner, and there is a square root involved, and moreover this d is called as the diffusion constant. Okay. So, and this tau phi inverse is called as the diffusing, or rather it is called as a dephasing rate, not diffusing, it is a dephasing rate. Okay. And how is this d coming into the picture? The d comes into the picture as the d this d is related to the conductance sigma via this relation that sigma equal to E square, this is electronic charge, and dN dE and d, okay, where n is the electronic density, and the dN d stands for the density of states. So, what we get here is that the conductance of a system is related to the diffusion constant and the density of states by this formula. Okay. So, the existence of a finite L phi, that, so if this coherence length is finite, so that distinguishes incoherent transport from a coherent transport. Okay. So, once again, just to remind you, the word coherent means that the electron actually preserves the information about the phase in moving from one point to another, and over the distance it preserves that information is known as a coherence length. Okay. So, this distinguishes between incoherent and coherent transport. Okay. So, there is another thing that is important here, is that this L phi and tau phi, they depend upon the temperature. T. Okay. And these temperatures, so basically with the increase in temperature, L phi and tau phi decreases, which means that the coherence goes down because of thermal effects, and it is easy to understand why that happens, because the number of collisions increase and the system actually undergoes through inelastic collisions at large temperatures because of thermal effects. And what we mean by inelastic collision is that the momentum is of course conserved in any collision, but the energy is not conserved. Okay. So, now it is very important that these L phi and the system length. So, the system length, let us talk about a linear dimension to be L, and this should have a relationship. You see, if L is much greater than L phi, that means that you have a large system and this system is much larger than the coherence length. If that happens, then the electrons will undergo many collisions. Okay. And when they emerge out from the other end, and you have attached electrodes or leads, and when they emerge out, there will be a large number of inelastic collisions which it has suffered, and in which case, so we understand that in that case the thermal effects will be dominant. The temperature will actually rule the transport, and we must be in the classical regime. Whereas, if we are in the opposite limit, that is your L phi is much greater than L, in that case you have the quantum mechanical features becoming important. So, here the classical effects are important, and in this case the quantum effects rule. Okay. So, along with that, there is another length scale that is important, which is called as a mean free path. So, just to remind you that the mean free path was discussed, or rather introduced by Drude in his model for electronic transport that gives rise to metals. So, if you start with a metal, that is if you have a metal and then this metal has free electrons. Now, if the electrons are completely free, then there can't be any resistivity, but we know that the metals have resistivity, and this is what your I square R, where I is the current and R is the resistance, that is equal to the power dissipated in the system, and that gives rise to Joule heating. So, this V into I or I square R or V square by R, all these are different forms of the power dissipated in the system. These kind of situations, so you need a scattering mechanism in order to bring in the notion of resistance, and that is what happened when Drude proposed that actually these electrons are otherwise free, but they undergo collisions, and between two such collisions they propagate like free particles. Okay? And not only that, he made one more very important comment there, and if you look at it carefully, it says that the electrons are completely randomly directed after any collision. So, the average velocity is 0, but the speed, that is if I ignore the direction, the speed of the electron after a collision is proportional to the local temperature of the system, and that is how he brought in the notion of temperature. So, a hotter region will emit or eject more energetic electrons. Okay? Now, that gave rise to these collisions between the electrons, that gave rise to the resistivity of this material, and the mean free path is the distance that the electron travels between two successive collisions. And here also it means the same thing. Let me write it with LMFP just to make sure that this mean free path. So, this is the distance that an electron travels between two successive collisions. Okay, so based on these length scales, let me define two regimes, and these two regimes are called as one is called as a diffusive regime, where let us also define another length scale which interatomic distance. So, that is basically the distance between two atoms or ions, and let us call that as A. So, this is the distance. Now, what happens is, so in the diffusive regime, your A is much smaller than LMFP, is much smaller than L, which is the dimension of the system or the system size, so to say, and which is less than L phi. So, there is a diffusive regime, which is what we have said, that where the conductivity is determined by the diffusion constant, and there is also a ballistic regime where A is much smaller than MFP, and this is of the order of L, and it is still much smaller than L phi. So, these two are the regimes that we need to consider for considering the conductance properties of the mesoscopic systems. Okay. So, in the ballistic regime, the conductance scale is set by these quantity called as a 2e square by h, and so we will see that as we progress that h over e square is equal to the unit of resistance, just the opposite of that excepting the factor 2, and this factor of 2 actually denotes summation over spins. So, there are up and down spins. So, these two factor of 2 represents that, and this is the unit of resistance, and this is the biggest triumph of quantum Hall effect, that it could actually the plateaus, the quantum Hall plateaus that we will see are completely quantized in unit of this. Okay. So, it is like h over e square, h over 2 e square, h over 3 e square, and so on and so forth. Okay. And so, this sets the unit of resistance, which is approximately 225.8 kilo ohm, whereas this e square over h also has a value which is inverse of that. Okay. We can write down that value also. So, the conductance has a unit. So, this is a unit of conductance, which is just the opposite, or rather inverse, not opposite, inverse, which is given by 3.874 into 10 to the power minus 5 ohm inverse, or you can call it as mho. Of course, there is another length scale which is often used, that is called as a localization length. And it could have been brought into the discussion, but it is not essential, because these are the two, primarily the two regimes where the conductance in mesoscopic systems are studied. But nevertheless, this localization length is the length over which certain observable or a physical quantity that falls to a value which is 1 over E. Like for example, this G, the conductance, which is equal to some G0. So, this is in presence of disorder. So, this is like minus L by xi, or maybe sometimes it is written 2L by xi. So, this G0 is the conductance without disorder. So, at a distance L equal to xi, which is the localization length, G falls to a value which is G0 over E. Okay. So, this is the definition of localization length. Now, let us derive a formula for the conductance, which is the next task that we have. This is called as a Landauer conductance formula. Landauer is a name of a scientist who's written it down, and so on. So, let us talk about this regime. Initially, let us talk about L greater than L phi, which means that this inelastic collision, and this is like, so there are collision with what? So, between the electrons and maybe with other electrons, maybe with phonons, maybe with impurities, disorder, defects, anything. Okay. So, this inelastic collisions will be there, and a classical transport will prevail. Okay. And what is meant by classical transport? Either you talk in terms of Drude formula, or you can also talk in terms of the Ohm's law. Okay. They mean the same thing. So, the temperature of the system decides what will be your tau inverse is decided by the temperature. So, what it means is that the temperature is large, which is a classical regime, and then tau inverse will be very small, which means the electrons undergo several collisions within the linear dimension L of the system. Okay. And in this case, of course, the Drude's law or for example Ohm's law to be valid. All right. Now, one is to understand that of course, we are not going to talk about this limit. We are going to talk about L to be less than L phi or even much lesser than L phi, such that the quantum effects are important, is the other limit that is important. All right. So, you have to understand that when you make a measurement of the conductivity or the resistivity, you need to attach leads. Okay. And this is what is done in the labs, in all undergraduate labs or the labs that you all have attended. It is done by either a multimeter, where you put those two the leg or the leads and then on both sides of the sample, and then you take the measurement. Okay. The multimeter gives you a reading, or there are more elegant way of doing this. There are 2 probe methods and there are 4 probe methods, which so you actually measure current by sending current in along 2 directions and measure the voltage along the other 2 directions. That is a 4 probe, and in a 2 probe method you measure it in whichever direction you send the current, you measure the voltage in the same direction. All right. So, we are going to attach leads, and these leads are very perfect metals, near perfect metals. Okay. So, which we will call as ideal conductors. So, in order to derive that, let me draw a schematic diagram which will help you understand that. So, this is like a sample. So, this is the whole setup, not a sample, the sample is here. So, we will call this sample as scattering regime. Okay. So, in the sample all the scattering happens, and as I said earlier that the scattering does not only mean electron scattering, it could be between electrons and impurities, electrons and disorder, electrons and phonons and various other things. Okay. And now, this is the ideal conductor or the electrode or the leads. Okay. So, this is an ideal conductor. There is one lead and this is the other lead. Think in terms of the multimeter probes that you attach on 2 sides. So, these are those leads that are there, and there is a bath. Okay, and there is a bath there, which bath means that they have a large number of electrons. So, they are the bath of electrons. So, if the electrons actually go from towards the right or towards the left, the electron density in the bath is unaffected, and as well as the temperature of the bath is unaffected, and that is like saying this bath means nothing but the battery or the bias voltage that you connect it to. Okay. And just as an example, let us say that this is the mu A is the chemical potential of conductor 1, and mu B is the chemical potential of these ideal conductor, which is the other lead or the electrode. So, lead and electrode, they mean the same thing, and there is a mu 1, say for example, which is the chemical potential of bath on the left, and there is a mu 2 which is the chemical potential of the bath in the right region. So, just to remind you that mu is a chemical potential, and the chemical potential is the energy that is required to add one electron in the system. Okay. Now, you could say that in a system of fermions, you could only add an electron only at the Fermi energy at t equal to 0. Okay. If you are not at t equal to 0, it will be some other energy which is slightly bigger than the Fermi energy, because the Fermi energy or the Fermi surface loses its meaning at finite temperature. So, why is this chemical potential a finite quantity? Why can't you just add one electron to the system without spending any energy? Why is it not 0? And it's not 0 for the simple reason that all the other electrons, the n electrons that are already there in the system, they have to readjust in order to come to equilibrium with this new particle or this new electron being added to the system. Okay. So, there is certain amount of energy cost, and that is the chemical potential. And if you want to understand it simply, then you take this nice distribution which is a Fermi distribution for electrons, and it is a step function. So, all the states below certain EF, let us write it with an epsilon, which you are probably more familiar with, and this is the epsilon f. Okay. So, that is the Fermi energy. So, if you want to, all these states are filled, okay, with one quantum state is being occupied by at the most 2 electrons, one spin up and spin down. So, you need to, if you need to add one electron more, you will have to add it here. Okay. There is no other way, because all the states are filled, and because of the Pauli exclusion principle, they are not going to take any more electrons. All right. So, in this thing, let me show that there are these modes called n. Will tell you what these modes are. There is a mode called m, and the reflection amplitude is, let us call it as Rmn, and similarly you have a Tmn. So, what these modes are? These modes are the allowed energy levels of the system of the ideal conductor. So, when an electron goes from left to right and it incidents on these boundaries are, let us say, labeled as A, B, C, D. So, we have sort of 4 boundaries. So, then an electron with energy n can get scattered into another level called m, which is either it is called mode or it is called channel. So, n and m are modes slash channels. Okay. So, there are different modes or different channels that are present in the system, which are the electrons dispersions, and so it represents a system comprising of a scattering regime which is sandwiched between 2 ideal conductors, which are leads or the electrodes, and in the ideal conductors the electrons are assumed to be free, and the wave functions are written as a product of, so this is important, this is your, let me also set the scale, the coordinate axis, so to say. Okay. So, we write down the wave function of this system to be a product of phi n y. Now, that is the y direction, which is what I showed here. This is the y direction. So, in y direction the system is not infinite. So, I have taken a strip of the system, okay, and in the x direction you can think of it as infinite. So, in the x direction, of course, this is going to be a exponential I k n x. So, the total wave function is going to be the product of these phi n y and exponential I k n of x. So, this is equal to psi n of x y, and you can put a plus minus here. Plus would correspond to sort of moving towards the electron moving towards the right, and minus may correspond to something moving towards, or the electron moving towards the left. And this thing comes because exponential I pi equal to -1. So if you add to say exponential ix, if you add a exponential ix plus pi, then it becomes equal to exponential minus x. So this gets, the phase gets reflected. So there is a kx there, which I forgot. Okay, so this thing, and so this becomes, it's reflected as a exponential minus I kx. Okay, so this is, and there is a normalization which is given by Kn, where Kn is equal to root over 2m E minus En divided by h cross square. So this En, these denote the modes or the channels. So this is the wave function, and I have used 1 by root over Kn as the normalization constant. So this is the wave function. So an incoming wave psi n plus from the left, once again let us go to this, from the left of the scattering region, it incidents at this B, this region that distinguishes between an ideal conductor and the scattering region. So it is partially reflected into a psi m minus. Okay. So a psi n plus is incident from left, and it scatters as psi m minus is reflected. So this is on the surface B, or the surface that divides the scattering regime with the ideal conductor, and so on. So what is this E here? This E is nothing but equal to the variable energy of the problem, that is E equal to coming from the bias voltage. Okay. So very similar scenario emerges at this C as well, and there will be a reflection towards the left, and there will be a transmission towards the right. Okay. So these Rmn and Tmn are reflection amplitude and Tmn are transmission amplitude. Okay. So then what happens is that your total transmission is in the channel n, or with energy En, is the sum over all the m's, all the other m's, and Tmn mod square. So the amplitude mod square gives you this transmission coefficient, and the conductivity is proportional to the transmission coefficient. Okay. So now if you consider NR channels, total of NR channels in the right and NL channels on the left, okay, on the right and on the left, then you have a S matrix which can be written as R T prime, T and R prime. So I sort of am assuming that you know what is S matrix. S matrix is in this barrier transmission problem, you write down these the coefficients here A and B, this coefficient as C and D, and let this coefficient be F and G. So there are these 2 by 2 matrices that connect AB and CD and CD and FG, and these matrices are governed by certain general properties, and these matrices they are unitary matrices, and they are related to the scattering matrix. I am skipping that discussion here, but we will probably come back later. And R and T are the reflection and the transmission coefficients for these ideal conductor, these two ideal conductors. So, actually it is TMN is getting transmitted, but something is getting reflected also. So, there is a TMN here as well, which is towards this, okay. And we will call for the second ideal conductor, we will call this as TMN prime, and so that is the prime. So, these two are the R and T, they correspond to the ideal conductor on the left, and R prime and T prime they correspond to the ideal conductor on the right, okay. And this S matrix, because of this, has a dimension which is NL plus NR multiplied by NL plus NR, okay. So, if you call this as N, this S matrix is a N cross N, where N denotes the total number of modes that exist, okay. And what is your mu 1 and mu 2? So, mu 1 and mu 2 is nothing but EV, okay. So, that is the biasing voltage. So, what you have done is that you have biased it here. So, you have biased it here, okay. So, it is like this, okay. So this is a voltage V. I did not want to draw it earlier, but the understanding is the same, that these baths are connected to battery, okay. So, this mu 1 minus mu 2 equal to EV, and then we have this DIN. So, that is an elemental current in the nth channel from left to right is written as rho n Vn and Tn, which is the transmission coefficient, which is a function of this biasing voltage, and this is also the Fermi distribution function, which is E minus mu 1 and dE. So, that is the current that flows from left to right. From left to right, that is the current. So, what is rho n? Vn is basically the velocity, and rho n is basically the density, which is equal to 2 pi h cross Vn. So, rho n and Vn would cancel, and what eventually you will get is that din L by R is equal to E over pi h cross Tn of E, okay, and f of E minus mu 1 and dE. Similarly, you will get a din R2L is equal to E by pi h cross, the 2 will cancel, and now you have it as 1 minus sum over m, because it is at the other junction which we have called it as C, at the junction C. So, this is R mn prime and square, okay. So, this is and then of course, E minus mu 2 and dE. So, this is the current that is flowing from right to left, and the other current, the one that is here, is from left to right, and this is right to left. So, the net current will actually be the difference of 1 minus 2. So, the net current, it is 1 minus 2, okay. And in calculating that, we can have we can see that it is E minus mu 1 and E minus mu 2. These are the respective chemical potential, and this is like a minus del F del E. I leave it to you to figure out that this is indeed equal to this, where I have done a Taylor series expansion of F about the energy E. So, the total current is equal to mu 1 minus mu 2 divided by pi h cross, and then dE and a minus del F del E and sum over Mn and Tmn E mod square. So, this is the current expression and that will give rise to the conductance. So, the conductance will be I over V. So, we divided by this V is equal to mu 1 minus mu 2 divided by E. We have said that earlier. So, when we divide it by that, your G becomes equal to a dE minus a del F del E and a trace of T dagger E T E. Okay. And so, at very low temperature or at 0 temperature, at very low or at 0 temperature, the del F del E is nothing but a delta function, which you understand because once again this is like this. So, it is everywhere 0, but here it is infinity. Okay. So, because there is a discontinuity there. So, that gives you that at low temperature or at 0 temperature. So, this is equal to 2 E square by H trace of T dagger E and T of E. Okay. So, this is called as the Landauer formula and this is what we wanted to find out. And so, this is the conductivity given in terms of the transmission amplitudes which are T. So, this is T dagger and as I said that these T's are matrices which are 2n NL plus NR cross NL plus NR. So, it is like n cross n matrices and so on, and this 2 is coming for the spin degeneracy. Okay. And it is a very good formula because it takes into account the effect of the contact resistance between the electrodes and the system, which is the scattering regime. Okay. So, the electrons actually enter from left to right from the electrode to the scattering regime and they see a different environment and that environment actually scatters them. Okay. So, this gives you, so basically the trace of T dagger T, it gives you the number of modes. And this number of modes will depend of course on the Fermi energy, and as the system is driven the Fermi energy rises. So, it accommodates more and more electrons and so this there are further conducting channels that open up. In general this G is actually even in presence of a magnetic field, this G is actually even. Okay. So, what we have seen is that we have taken a sort of experimental system where you have sort of a material whose resistance you are going to find out. So, you will put leads and you will put battery. The leads are the ideal conductors and the battery drives the system. It supplies electrons, it sort of manipulates the Fermi energy, and in this condition we have seen that it is like a simple scattering problem of electrons across a boundary, and that gives rise to this nice formula which is called as the Landauer formula. Okay. As I said that this is very general, okay, it is not restricted to Hall effect or quantum Hall effect, but we will see that this is a general scheme of calculating resistance or conductance of a mesoscopic system, which we will be talking about throughout this course. Okay.